Welcome back, everybody. Today, we're going to be continuing our saga of single-qubit universal quantum computing. So the main purpose here is I want to be able to provide a gate set for you that we can prove is actually universal. Now, this gate set isn't going to be the final form that we'll want to take, and we're building towards that right now. And in particular, just to remind you where we are, let me share my screen and jump over to my now hopefully blank slides. What we have is again, a very simple computational model for a single qubit quantum computer. These are the things that we're allowed to do. One, we can prepare a qubit in the state 0. Two, we can apply the following gates. And so the gates, again, are the identity, which is described as a unitary transformation, just like the rest of these. Y, Z, Hadamard, the phase gate. I'm also going to include a new gate that I hadn't discussed last time, which we'll call the T gate. The T gate here, this guy is defined to be the square root of the S gate, which is the fourth root of the Z gate. And this is equal to the matrix 1, 0, 0, e to the I pi by 4. Okay, so those are the first set of gates. Now, these ones over here, these are known as Clifford operations, and they form, as mentioned last time, a finite gate set. So it turns out they are not universal for quantum computing. These Clifford operations, however, if we combine them with the T gate, and in particular, one of the things that we're working towards is showing that Hadamard and T are universal for QC on one qubit. And as intermediate gates that we're going to need in order to be able to get to this point where we can show that 2 gates alone are sufficient to be able to do single qubit quantum computing, we're going to end up introducing 2 very useful concepts. First is the RZ rotation, and the second is the RX rotation. And both of these operations, and this is, I guess, theta, both of these are of the form e to the negative I z theta divided by 2 and e to the negative I x theta over 2. Now, these 2 operations are continuous operations, meaning we assume that for every theta, there exists a gate of the form RZ of theta. So this is, you might ask, okay, well, why not just take, if these 2 operations seem like they're very powerful operations, why not assume that our quantum computer just has them? Well, there's good reason why we shouldn't assume that our quantum computer has them. And we'll get to this much, much later in the course when we talk about quantum error correction. But the basic idea is that, let's say what we had is we wanted to be able to do an RZ rotation for an angle of theta, right? Well, the way that we practically want to do this is we would like to be able to figure out when we actually make an error in this. And so a simple example of an error that we could consider would be, instead of doing RZ plus theta, we could consider doing RZ plus epsilon, or theta plus epsilon. So this might be, okay, well, if this is the value of theta in here, we might actually end up, ideally, we'd like to maybe apply this rotation. Instead, what we could end up doing is we could end up applying that rotation just a little bit away, like epsilon far away from the target that we want. Now, in the event that we have a discretized set of rotations, then for any particular state that we start in, then there's a possibility that we can error correct, because we can tell the difference from the quantum state, which has been rotated the ideal angle plus epsilon, and the next discrete rotation that we'd like to carry out, because, well, that rotation is closer to the target. So this is one of the things that's really essential for quantum error correction, that basically if we ended up having the other situation where any angle was legal, we would be unable to distinguish just by measurement whether or not we'd intended to do this rotation or this rotation plus epsilon. So breaking up our allowable rotations into a set of discrete bins allows us to distinguish them and also determine when an error occurred in our attempts to try to implement that rotation. So this is the basic idea behind how we try to do it, and why it's so vital for a quantum computer to end up using a discrete set of gates. Because if we don't have a discrete set of gates, then theoretically there is absolutely no way that we can correct tiny errors in the implementation of those gates. So this is why we're working towards this. And well, I should mention, of course, the final thing that we of course need is measurement. And we've described many times how measurement of this one qubit ends up working. But these are the elements that we're going to be putting together, that we have in our computational model, and we're going to be proving that these are universal. Okay, so very first step. What we would like to be able to do is we would like to be able to show that RZ plus RX is universal. Universal. Okay, by which I end up meaning that a gate set is a set of unitary transformations in some finite dimensional vector space. Okay, so that's what I mean when I define a gate set, and we'll describe this gate set with the symbol G. Okay, so then the basic idea is that the definition of universality is def G is universal if and only if for all unitary matrices U in C2 to the n by 2 to the n and epsilon greater than 0, there exists a value of n and a sequence, let's call it Q sub j, where j is equal to 1 through n, such that the norm of this unitary matrix minus a product from j equals 1 to n of elements in this set is less than or equal to epsilon. So visually, what this is saying is that if we've got a unitary transformation over here that we would like to carry out, then what there exists a discrete set of gate operations. Let's imagine these are our gate operations. So this would be like GJ1, GJ2, GJ3, GJ4, GJ5, GJ6, such that this ends up leading the product of all of these different unitary transformations, ends up leading to a unitary that's within distance epsilon from our target. Now, what this also ends up meaning is because of the fact that, any unitary transformation can be closely approximated, this also ends up meaning that any state transformation can be efficiently performed. For example, we can always end up saying that this transformation, there always exists a unitary transformation mapping psi to phi. Okay. And in particular, you can end up seeing this because that unitary transformation, if we write this in Dirac notation, this unitary transformation can always be written as phi psi plus some state phi perpendicular, psi perpendicular, at least for the 2D case. Okay. And you can very easily end up seeing that if phi perpendicular phi has zero inner product and psi perpendicular psi has zero inner product, that this transformation is unitary. So moral of the story is that we can always end up building a unitary to do any state transformation we feel like. And in turn, because of this, if we need to prepare an arbitrary state, we can always build a unitary that will prepare any state psi. And we'll see an explicit construction of this in just a moment. Okay, so this is what I end up meaning by universality again. So the main theorem that we're going to be showing today is the following. For all unitary U in C2 by 2, U is equal to e to the I alpha r z of beta r x of gamma r z of delta for some alpha beta gamma delta inside the interval 0 to 2 pi. Okay, so what this basically ends up saying is that what we can do is we can carry out a rotation, a z rotation, an x rotation, and a z rotation. And these 3 rotations will be sufficient for us to be able to implement an arbitrary rotation. And for those of you who might have seen this before, this form looks very similar to what's known as Euler angles. It turns out that it essentially is the same idea, which comes about because of the fact that there's a strong relationship between the group of 2 by 2 unitaries and and O3. In fact, it forms a double cover. So that is the reason why an Euler angle transformation can be used to build an arbitrary 2 by 2 unitary transformation in exactly the same way that it can be used to build an arbitrary rotation. The biggest difference is this overall phase. Now, I'll argue later that this overall phase turns out to not matter, but we need it in order to be able to formally state this without having to worry about these dynamically irrelevant overall phases for it. But let's worry about that later. For the moment, let's begin by just showing this result. So this result, the proof of this is actually kind of straightforward, conceptually speaking, because all it involves doing is actually just plugging into the definitions of these rotations and verifying that you can do it. So let's begin by looking at this. In matrix representation, we can write this as e to the negative I beta over 2, 0, 0, 0, cosine gamma over 2 minus I sine gamma over 2 minus I sine gamma over 2 and cosine gamma over 2. Okay, and oh, I wrote 0 here for some reason. I meant e to the I beta over 2. Got a little 0 happy when I was drawing that in. So then we've got the delta rotation, which is e to the minus I delta over 2. 0, 0, e to the I delta over 2. Now, let's multiply all of these through. This is equal to e to the I alpha, row 1 times column 1, which is e to the negative I beta over 2, cosine gamma by 2, negative I e to the negative I beta over 2, sine gamma over 2. Now, next we multiply the bottom ones and we get negative I e to the I beta by 2, sine gamma by 2. And finally, we end up having e to the I beta by 2, cosine gamma by 2. And last but not least, we still have this minus I delta by 2, 0, 0, e to the I delta by 2. Now we've got to multiply these matrices again, and this gives us e to the I alpha, e to the negative I beta by 2, e to the negative I delta by 2, cosine gamma by 2, and that component is 0, then we end up having negative I e to the minus I beta by 2, e to the I delta by 2, sine gamma by 2. From first row times second column, now we have minus I e to the I beta by 2, sine gamma by 2, e to the I beta, sorry, this is e to the negative I delta by 2, sine gamma by 2. And then finally, we have e to the I delta by 2, e to the I beta by 2, cosine gamma by 2. All right. And so this is the this is our final expression for the matrix. Okay, so I'll just copy and paste this onto the next slide because it looks like we've kind of run out of space here. Oh, whatever. It's a good enough copy paste job. It's good enough for government work. Okay. So that is the matrix that we end up producing. What we would ideally like is we'd like to be able to choose this matrix in such a way so that we can build a unitary matrix that maps 0 into any state, some arbitrary state psi that we feel like. That's equivalent to saying we want to specify the first column of this matrix. And so that column for the arbitrary state psi, let's just choose it. So it's of the form A 0 plus B 1. And of course, in order to make this a valid quantum state vector, we have to have that the probability, total probability is 1, meaning that absolute value of A squared plus absolute value of B squared is equal to 1. And just to remind you, these are complex values. So these are in C, okay, subject to this constraint. Now, if we have this, then what do we have? Well, we end up having, just by equating this, we have that U acting on 0 is just U acting on 1, 0. And then by matrix multiplying all of these guys, we end up having that this is equal to cosine gamma by 2, e to the I alpha minus beta over 2 minus delta over 2 for the first component. Then, of course, for this guy, we have sine gamma by 2. And then we have e to the I alpha plus beta by 2 minus delta by 2. And then we have minus pi by 2. You might wonder, why the heck is there a minus pi by 2 here? Well, using Euler's identity, it's easy to see that e to the negative I pi by 2 is actually equal to minus I. And so this extra factor of minus I over here, I've just brought it up into the exponent by using Euler's identity. So this is equal to, of course, or we would like this to be equal to A and B. Now, I'm going to further define this to be equal to, without loss of generality, absolute value of A e to the I don't know, theta A, absolute value of B e to the I theta of B. And so this is just taking advantage of the fact that complex numbers can always be written in polar form. So I've got the magnitude stored here, and I've got the sign, or more generally, the complex phase of that number stored here. So in general, if you recall, any value of z, which is a complex number, can be written of the form r e to the I theta. And of course, where r is a positive number, and r is greater than or equal to 0, and theta, of course, we can pick between 0 and 2 pi if we feel like. So if we by using this, we can always end up seeing that without loss of generality, this expression is valid. So we can see right off the bat what the angles are. By dividing the absolute value of the two components, we end up seeing immediately that sine gamma over 2 divided by cosine gamma over 2 is equal to the arctangent, or sorry, skipping a step here, is equal to absolute value of B over the absolute value of A. And this ends up implying that it suffices to end up picking gamma is equal to twice the arctangent of B over A in absolute value. Okay, so that gives us one of the particular values. However, we need more information in order to be able to figure out what the rest of the unknown parameters are. In particular, we'd like to know what beta and delta are, as well as alpha, I suppose. So the next thing we're going to do is just take a look at these angles. From these angles, we demand, if equality is reached, that we don't just match the magnitudes, we also need to match the phases. So matching the phases here and here, we end up getting two equations. The first is that theta A is equal to alpha minus beta over 2 minus delta over 2. And the second equation, of course, comes from here, which is theta B is equal to alpha plus beta over 2 minus delta over 2. All right, and so we can go through these and actually solve. So the first equation ends up telling us that alpha then can be chosen to be equal to theta A plus beta plus delta divided by 2. And similarly, the second equation ends up giving us that beta is equal to 2 times theta B minus beta over 2 plus delta over 2. Okay, which of course we can substitute in, and this just ends up giving us twice theta B plus theta A oh, sorry. Okay, I need to still subtract off alpha. Okay, and so I won't bother with the substitution, but we can substitute in the value of alpha in for this expression, and we'll end up getting a unique value of beta that ends up satisfying this, that only ends up depending on delta. And so from this, we figured these two equations, we figured out what alpha and beta are, as well as we've got an expression for gamma. However, these three variables aren't enough in order for us to be able to isolate for what delta is. So we need an extra piece of information. So the extra piece of information comes in from the homework problems. So from the homework problems, we ended up showing in it, or you will end up showing, that every column in a unitary matrix is orthogonal to the others. Okay, now we have a 2x2 matrix here. And because it's a 2x2 matrix, this ends up implying that there exists a unique orthogonal vector, again, up to a scalar multiple of A0 plus B1. The reason why is that a two-dimensional vector space of the form like AB is spanned by at most two orthonormal vectors. For example, right, in the simplest one is that we can span the space by the vectors 1, 0 or 0, 1. Alternatively, we could rotate our basis and end up doing something like 1, 1 over root 2, 1 minus 1 divided by root 2. But the moral of the story is, once we've done this, there's no way we can squeeze in a third linearly independent vector inside a two-dimensional space. So therefore, once we've identified this one vector, then there's only one other choice up to a scalar multiple for the next column. So what that ends up meaning is that it turns out we can write column 2 as a state of the form B all right, let me just if this is in this form, we can end up writing this as absolute value of A e to the I theta A 0 plus absolute value B e to the I theta B 1. Given that, the second column can always be written in the form absolute value of B e to the I theta A 0 minus the absolute value of A e to the I theta B 1. And so in order to see that they're orthogonal, oh, and let's put in an additional multiplicative factor, e to the I chi over here. Now, I said up to a scalar multiple. The reason why in general it can be written in this form is because of the fact that we demand that this is a unit vector. So if because this over here by construction is already a unit vector, because its length is absolute value of A squared plus B squared, which we've hypothesized is equal to 1, this vector is already a unit vector. So that means we can't multiply it by something that isn't of unit length while keeping it to be a unit vector. So if we write this extra factor that we're multiplying by in the form r e to the I chi, we demand then that the absolute value of this is equal to 1. And this implies that r equals 1 because r is real valued. So therefore, without loss of generality, we can always write every unit vector for the second column in this form. But in order to see that, we actually just need to compute this inner product and verify that my guess about this orthogonal vector is correct. And so what we end up getting is the following. And now note that what I've done is, in order to compute the inner product with this and the original vector, I've taken the adjoint, which is why the minus sign is here. Minus, oh, this shouldn't be an A here, should be that. Minus 1, absolute value of A, e to the minus I theta B, all multiplied through by 0 times absolute value of A, e to the I theta, plus 1, absolute value of B, e to the I, and that's theta A, e to the I theta B. Okay, now just multiplying this through, we end up getting the result is A, absolute value of A, absolute value of B, minus absolute value of A, absolute value of B. Oh, I also need to include an e to the minus I chi times e to the minus I chi, which of course is equal to 0. Therefore, this vector, as I claimed, is actually orthogonal to the other ones, and is up to this phase, e to the minus I chi, is the only choice that we can end up making for that second column, given that we end up constraining the first one. So that is how it goes. Now, the next thing that we end up needing in order to be able to show this is we need to be able to show that the that we can end up with our series of 3 rotations, that we can choose the parameters for this column here to end up giving us the appropriate vector. So in order for us to be able to do that, well, what do we have left? Well, let's just take a look at the what we would like to build from it. So actually, yeah, I think I might even still have it. Yes, I do. Okay. So what we would like to do is we'd like to say, okay, well, if that's true, then we have that absolute value of B e to the minus I or plus I theta A okay, let me just make sure that this is right. So we want to get the second column here, and first element of it will be, yeah, okay, cool. So then this is going to be equal to e to the negative I, e to the negative I beta over 2, e to the I delta over 2, sine gamma over 2. And when we go through the math in order to be able to solve it, recall that we already know what this guy is over here. Oh, and this is e to the negative I, or e to the plus I chi here. We already know what this is. We've chosen this particular value. This is a free parameter. So we can end up picking this in order to be able to solve for chi. So in particular, what we end up getting is we end up getting at the end of all of it that our choice of delta is equal to something like theta A plus chi plus pi by 2 plus theta B minus theta A over 2 plus pi by 2, which can be simplified, no doubt. And so this ends up showing an explicit value of delta. And then by back substituting, we can end up finding the rest of the parameters, alpha, beta, gamma, delta. And without loss of generality, these can be chosen to be inside the branch 0 to 2 pi, because of the fact that all of these rotation angles that we end up getting afterwards can always be re-rotated back inside those without changing any of the overall quantities. So that's not a problem whatsoever. So this ends up showing that what we can do is we can pair an arbitrary a matrix that has an arbitrary first column and has a second column that has an arbitrary vector over here. The only thing that we technically haven't shown, so we can build every matrix of this particular form, but we haven't shown that it's unitary. So one fun fact that technically, I mean, it should be really obvious in a way, but we sort of kind of need to show it, is the following lemma. Let U B, comma V, be unitary. Then UV is unitary. Okay, proof. And the proof for this is straightforward, right? For what it means for a matrix to be unitary is that its adjoint is its inverse. So let's take a look at UV dagger times UV. Now recall that the adjoint ends up reversing the order of the product. So the adjoint of this is equal to V U dagger U V. Now, because of the fact that matrix multiplication is associative, we can end up expressing it like this. Now, since U and U is unitary, this is equal to V dagger V, and this is equal to identity. And then clearly, as a corollary, the product from j equals 1 to n, U sub j for unitary U sub j is also unitary. Okay, and the proof by this is a straightforward argument by induction. Okay, so this means that the product of unitary matrices in general is unitary. Ergo, this over here is also a unitary matrix. Why is that? Well, because of the fact that this is composed by the product of 3 unitary matrices. The product of unitary matrices by this argument is unitary. So therefore, this is not just an arbitrary, matrix. This is a unitary matrix, and hence what we've done is we've described any arbitrary unitary matrix that has any first column we feel like. Ergo, any unitary matrix like this, any 2x2 unitary matrix can be written in this particular form. So this ends up showing that RZ and RX are universal for 1 qubit quantum computing. So I should mention one final thing as a little bit of an aside, but I mentioned that the e to the I phi alpha in front of this actually turns out to not really matter. Here's why. Let's assume that I've got 2 unitaries. I've got a unitary U, and I've got a unitary e to the I alpha U. Now, let's say we want to compute some probability of this. The probability p sub x is just going to be equal to x U0 versus x e to the I alpha. And this is, of course, absolute value squared. E to the I alpha, u0, absolute value squared. So I'm taking a look at the probability, given we start in a state 0 without loss of generality, of getting an outcome in state x. For both this case with a e to the I alpha in it, and the case where it's absent. Now, because e to the I alpha is just a number, we can move it either side of any of the linear algebraic operations in this probability calculation. So this over here can always be written as e to the I alpha x u0, absolute value squared, which by the definition of the Euclidean norm is e to the I alpha, absolute value squared, absolute value of x u0, absolute value squared, which is just equal to px. So you can see that every probability that we end up writing down is exactly the same, whether or not we have this e to the I alpha. Another way of writing it, or understanding this, is that this e to the I alpha is actually just an artifact of our representation, and it doesn't play any role in the fundamental description of what the probabilities of outcomes are. It's just unfortunately needed in order to make sure that when we compute the norm of two matrices, like we computed the norm of the difference between, let's say the matrix 1, 0, 0, 1, the identity, and e to the I theta, 0, 0, e to the I theta. Well, the norm between these two is equal to, in this case, the absolute value of 1 minus e to the I theta, which I think actually ends up turning out to be something like twice cosine theta over 2. This, you can see, is not 0, even though these two matrices, from the perspective of quantum theory, predict exactly the same thing for every outcome. So this is one of the reasons why we have to be careful with the definition to make sure that, we count whatever overall totally unnecessary phase is included in the definition of these transformations, even if it doesn't end up affecting the underlying statistics. And this phase over here is often known as a global phase. And the same argument ends up holding for a quantum state, that the quantum state psi is equivalent to e to the I alpha psi. Because when you go through all of this, you'll see just the same that this extra factor of the phase doesn't matter one iota for computing the probabilities. So, well, you'll hear me mention this term global phase from time to time, and that's all I mean. It's just this representational artifact where the unitary matrix and the state vector are only really defined up to some constant multiplicative factor. And you can actually, in principle, just choose this in order to make your math easier. And in a couple of cases, we'll show how a good choice can actually make our lives a lot easier. But for now, yeah, let's just treat it like it's some property that we want to match in the matrices. So yeah, this shows that we can do exactly that we can end up matching any arbitrary unitary matrix that we would like to build, which in turn shows universality on a quantum computer for 1 qubit. However, the next step, and slightly trickier step conceptually, is to end up showing that we don't need to have these continuous variable rotations, that instead we can closely approximate the RZ and RX operations through a sequence of Hadamard T gates. And that will be the subject of our next lecture. Thank you very much.